MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this clip, we will continue our discussion of discrete probability distributions. We have already met one of them, namely the binomial distribution, and in this clip we will be discussing another important discrete distribution, namely the Poisson distribution. Let's look at the context in which this distribution arises. In many practical situations, we are interested in measuring how many times a certain event occurs in a particular interval. That interval could be an interval of time or an interval of length or area. Some examples: I may be interested in knowing what's the likelihood of a certain number of phone calls arriving at a call center in 1 hour, or the likelihood of a certain number of customers arriving at a toll booth per day, or the number of flaws in a length of fiber optic cable. So for the first two experiments, you can see that the interval is one of time, but for the third experiment, the interval is one of length or space. Okay, so we're interested in counting the number of events. So clearly these are discrete outcomes. You could have 0 events, 1 event, 2, 3, and so forth. And you can also see that based on the description of the experiments given here, that this is not just a discrete random variable, but a countably infinite one. Alright, so I can identify each specific outcome. For example, I could say that 0 phone calls arrive at the call center in 1 hour, 1 phone call, 2, 3, 4, so forth, all the way up to infinity. Now, as a practical matter, you probably wouldn't get more than 500-600 calls an hour, depending on how many staff members you have, but theoretically the number of phone calls you could get ranges anywhere from 0 to infinity. Hence, this is not just a discrete random variable, but unlike the binomial distribution, this is a countably infinite type of random variable. Now, if the experiments meet the 3 conditions listed at the bottom over here, let's look at each of the 3 requirements. The length of the interval must be fixed in advance. So am I talking about the number of phone calls received in 1 hour or 1 day? What is the period? Is it a kilometer of fiber optic cable or 10 kilometers of fiber optic cable? So the length of the interval over which I'm counting the number of events, that interval must be fixed in advance. Second, the average rate of the events over this interval must remain constant. In other words, the average number of flaws for the fiber optic cable shouldn't change as I go from one part of the cable to another. Similarly, if I think about the number of phone calls received at the call center in 1 hour, the underlying average rate should not change as I go from the first minute to the 60th minute of that hour. Third, and this is a very important one, the number of events occurring in disjoint intervals are statistically independent. What does that mean? It means that the number of calls that I receive at the call center in 1 hour is statistically independent of the number of calls that I would receive over another 1 hour period. So if I take 2 1-hour periods at the call center, the number of phone calls that I would receive during those 2 1-hour periods are independent of one another. Okay, so if these 3 conditions hold, then the random variable, in other words, the number of successes, the probability of the number of outcomes, is given by the Poisson distribution. So in this case, probability of x equal to k, in other words, the probability of k successes in this interval, whatever we define the interval to be, is given by e to the minus lambda, where e is the natural logarithm base, which is 2.718. Lambda is the average number of successes in that interval. It's the average rate, okay? And k is the number of successes that I'm looking for. So e to the minus lambda, lambda to the power k divided by factorial k. Now, I will not show you or go over the mathematical derivation, but the mean and variance of the Poisson distribution is both lambda. In other words, the expected number of successes in that period is lambda, and the variance is also lambda. Okay, so let's see how one would apply the Poisson distribution to an actual example, actual problem. So let's say the number of flaws in a fiber optic cable follows a Poisson distribution, and you're told to assume that, and there is some empirical basis for making that claim. But for this problem, in any case, the average number of flaws in 50 meters of cable is 1.2. So this is a lambda that's given to you. The average number of cables in 50 meters of cable is 1.2. So the interval is 50 meters. Okay. So the first problem asks, what is the probability of exactly 3 flaws in 150 meters of cable? So do you see that the interval has changed? It is no longer 50 meters. It is now 150 meters. Therefore, I immediately have to change lambda. Lambda is the average number of flaws over the interval. Since the interval is now 150 meters, the average number of flaws would be 1.2 times 3. So I would expect 3.6 flaws on average over the 150 meters of optical fiber cable, given these parameters. So what is the probability of exactly 3 flaws? The built-in Excel function is Poisson, and you can see that it has 3 input parameters. The first is, how many successes are you looking for? I'm looking for 3 successes, exactly 3 successes. So 3 flaws in this case. Observing a flaw is a success. The probability of 3 successes. What is the average for the interval? In this case is 3.6. It is not 1.2. It's very important to get the interval right. I'm looking for 3 successes in 150 meters of cable. Therefore, the mean I should use should be the mean for 150 meters of cable, not 50 meters, okay? And just like the binomial distribution, since I want the height of this one spike, x equal to 3, the likelihood of exactly 3 flaws, I am not computing a cumulative probability, but rather the probability of exactly one outcome. I would put a value 0 over here. So that probability is 0.21. So the likelihood of exactly 3 flaws in 150 meters of cable is 0.21. Let's look at the second problem. It says, what is the probability of at least 2 flaws in 100 meters of cable? First, the average number of flaws for 100 meters of cable is 1.2 times 2, because for 50 meters of cable the average is 1.2. So now you have to do a little bit of manipulation here. The probability of at least 2 flaws, you can see, is the probability of 2 flaws plus the probability of 3 flaws, 4 flaws, 5 flaws, on and on and on, all the way up to infinity, which would take us a lifetime to compute. So we obviously cannot compute things this way. And we worked a problem similar to this for the binomial distribution. If I could somehow compute the probability of at most 1 flaw, so 0 and 1 flaw, and I subtract that result from 1, I'll get the answer that I want. So let's compute the probability of at most 1 flaw. So this would be Poisson. I'm looking for the probability of 1 flaw. The mean is 2.4, and this time I want a cumulative probability. Why? I want the probability of 0 flaws and 1 flaw in this 100 meters of cable. So this is 0.30. So the result that I'm looking for is simply 1 minus this guy. So the likelihood of at least 2 flaws is 0.69. I hope you saw how we did the computation. The built-in function Poisson does not give you the 2 or greater. It gives you on the left side from 0 on out. So that's why we first had to compute the probability of 0 successes, 0 flaws and 1 flaw, and then subtract that number, the total, from 1. Let's look at the third one. What is the probability of exactly 1 flaw in the first 50 meters of cable and exactly 1 flaw in the second 50 meters of cable? So we have 2 events over here, 50 meters and another 50 meters, okay? And remember, by the third condition of the Poisson distribution, these 2 events are independent. So if you have the joint probability of 2 independent events is simply the product of those probabilities. So let's compute the first one. The likelihood of exactly 1 flaw in the first 50 meters is Poisson 1 flaw. The mean is 1.2 now because we're looking at 50 meters of cable, and I'm not looking at a cumulative probability here. So that's 0.36. The probability of exactly one flaw in the second 50 meters of cable is also Poisson one flaw. The average is 1.2, and I'm looking at exactly that one spike. It's not a cumulative probability, so that third parameter is 0. So there I have it, 0.36, 0.36. Now, these two events, the first 50 meters and flaws in the second 50 meters, they're independent events by the third characteristic of Poisson distribution. So the probability of exactly one flaw in the first 50 meters and one flaw in the second 50 meters is simply the product of these two. Okay, it's 0.13. So I hope you saw how one goes about using the Poisson distribution and Excel's built-in function to compute Poisson probabilities. It is a discrete probability distribution, but one where the number of outcomes is infinite. So it's a countably infinite type of discrete distribution, and it's very useful for computing the likelihood of certain number of outcomes in an interval. Now, if you go back to the few examples that we had at the beginning of our discussion, the number of phone calls received in a call center, number of customers arriving at a toll booth, these calculations of the probabilities are not idle calculations. They are very important calculations that are the basis of staffing decisions. Okay, so if you want to be able to service a high number of calls, let's say you want to achieve 90% service rates, then you want the probability of you want to have enough staff on hand so that you can handle the calls, a high number of calls that will be arriving within that 90% likelihood. So these calculations using the Poisson distribution are very useful for counting, provided of course these three conditions that we have listed at the bottom are met.